Well, there we go. Okay, so hello everyone. You're being recorded now, so welcome back to the RL Theory Seminar for the fall semester. And as with all the other seminars, like feel free to just ask questions, like just unmute yourself, ask questions in the middle of the talk. And if you want to ask in the chat, you can do that too, and I can just ask the question for you at like the appropriate time. Also, there's going to be like a Q&A at the end of the talk, so as there usually is. So we'll be done in approximately like 50 minutes from the start of the talk, and then you can ask your like longer questions then. And today we'll have Nan being the technical co-host for the talk, so he'll stimulate the speaker with some technical questions. And yeah, and today we have our presenter, Reda Ouhamma, and yeah, so Reda has he's joined the Systems Control and Multi-Agent Optimization research team at EPFL now as a postdoc. And his interest is spanning between reinforcement learning theory, multi-arm bandits, LQR, multi-agent reinforcement learning. And prior to joining EPFL, he did his PhD degree at Enria's Lil's school team. And he did this under the supervision of Aldalric Millard and Vinay Pershu. And before his PhD, he graduated from École Polytechnique in Paris. And so, yeah, Reda, feel free to take it away and start your talk now.
Thank you, Vlad, for the presentation and the invitation. I'm going to share my screen now. Okay, so thank you everyone for being here. Today I will present my AAAI paper, which is Bilinear Exponential Family of MDPs, Sample Efficient Learning and Tractable Exploration. So this is a joint work with my supervisor, Odalric Maillard, and Deba Brota. This was done while I was at INRIA Lille. Okay, so a quick outline of that talk. First, I'm going to introduce the setting and some key challenges. Then I will talk about this bilinear exponential family of MDPs, why it's interesting, and what can be done with it. And then I'll introduce the algorithm, along with some interesting proof techniques that are used in the paper. Okay, so the setting is episodic reinforcement learning, where we have this tuple M of states, actions, probability, reward, and a number of episodes and the horizon of an episode. So in this case, we consider continuous states and actions. The interaction protocol is the standard one in episodic reinforcement learning. So at every episode, the agent chooses their policy beforehand, and then at every step, they use that policy to sample an action, then observe a reward from this reward mapping, and transit to a new state following this transition mapping of the MDP. The performance measure chosen in this paper is the standard value function, so non-discounted because it's an episodic setting, and the objective is to minimize the cumulative regrets. Okay, so we start by some challenges in episodic RL about continuous spaces and the popular linear reinforcement learning model. So the key challenges, the first one is the very famous one of exploration exploitation. I'm not going to talk in detail about this, since this is an RL seminar. I guess everyone is familiar with it. So this is traditionally addressed with the optimism principle, and you can see multiple references on this for theoretical analysis as well as some experimental evidence. Another challenge in RL in general and episodic RL in particular is when dealing with continuous state action spaces. So the problem in this case is that optimism becomes intractable because we have the double optimizations over continuous spaces that's not necessarily convex, all that kind of things. And so usually in literature, what we find is that this is handled with some additional structural assumptions about the value function or about the model. So the most popular one is the one introduced by Shijin, which is linear MDPs. There are also other ones like the eluder dimension and bilinear classes and many others that we saw in this seminar, for example, that we saw before, like the sail condition, another type of eluder characterization, and many others. And so the last challenge I want to talk about is planning in continuous spaces. So the problem in episodic RL is that we want to use the Bellman operator, but this Bellman operator is intractable because of this integral that needs to be computed basically for every stage and action.
Can I ask? So here, is it a typo that there's S tilde and S prime? Like they should be the same, right?
Yes, it's S prime. Sorry, yes.
And
yeah.
Also, what do you mean by intractable? Because exactly computing the integral may be intractable for general transition probabilities, but at least you can do like sampling, right? If all you need is to approximate this operator, like you could just for each essay, do a Monte Carlo approximation.
Yes, you could, but if you have continuous state and action spaces, you need to do it for every state action pair. So doing so is, I'm not sure you can do it in polynomial time.
Well, I think then you need a function approximation anyway, right? Because then eventually, how do you even represent the resulting value function? Well, you represent it in a parametric manner, right?
Yes, I agree. Yes. Yeah. This is why you need this. This is why structural assumptions were introduced. Yes. Yeah, I'm not challenging this structural assumptions. Actually, my paper is just another one of these structural assumptions. But yeah, I agree that they are necessary if you want to compute this term. Okay. So then I'll move on to linear MDPs. This is introduced just as part of the motivation for why we might want to explore other structures. So this is this popular model was introduced by Shijin, and then there were some variations of this model. So the initial model is where transitions and rewards are d-dimensional with some known feature map in phi. There is also a variant of this assumption where it's model free, so only the value function is linear. There is no assumption about the transition dynamics. But this was the original one, but they're both used in literature. So the benefits of using such an assumption is that it allows for closed form estimation, and also since the value function, so you can show that with this assumption the value function is linear, and therefore if we go back to this previous inequality, since this transition is linear and decouples the next state from the current state in action, then the current state in action can go out of the integral, and basically this becomes independent of SNA, thus computable. So this is a big benefit of using such a representation, which is why it was introduced. The limitation of this assumption is its expressiveness. So basically, this assumption of linear MDP subsumes tabular MDPs, but there aren't any other known examples of MDPs with continuous states that are also linear MDPs. Okay. So this is part of the motivation why we wanted to look at other structural assumptions, and we will introduce this bilinear exponential family as an alternative because it is expressive and it allows for sample efficient learning. Okay, so this is the definition of the bilinear exponential family of MDPs. It was introduced to the best of my knowledge by Chaudhuri et al. In 2021. Basically, it assumes that both the transitions, basically it assumes that transitions are in this bilinear exponential family, which means basically that it is an exponential family of distributions, and the exponent is bilinear in the next stage and the current stage and actions. And and this is assumed for rewards, for the rewards as well, where these features, these functions, psi, phi, and are known. The parameters theta are the unknowns, and this matrix m theta is this linear mixture of known matrices AI. And z in this expression is the log partition function, so the normalization factor. Okay. So why is this? Why is this family of MDPs interesting? The first reason is the expressiveness. So the BEF, bilinear exponential family for short, it captures, of course, tabular MDPs such as the other the linear MDP one, and also factored MDPs, which are MDPs where the transition of a variable or a subset of variables depends only on a certain subset of variables. And it also captures linear dynamical systems, which is when the next state is linear in the current state in action. And I want to emphasize that this is different than the linear MDP assumption that was before. Okay, so this is the first reason why it is interesting to consider this family. Now, the second reason is that it can lead to more tractable reinforcement learning. So basically, if we look at this transition function, we can see closely that it resembles the RBF kernel, the radial basis function kernel. And we can do so by just a simple transformation of this exponent to make appear a quadratic term plus some additional terms. And basically, since it is the RBF kernel, then we can write it as this scalar product between, so this is all of this is a function. So this is an infinite dimensional vector. And this is a scalar product in this RKHS that corresponds to the RBF kernel. Okay, but this linearity is not finite dimensional, so still we cannot use it to compute the integral that we said before. So why is it interesting? The reason is that thanks to random Fourier features, which were introduced in 2007 and analyzed in 2007, they show that it is possible to provide a finite dimensional approximation of these two infinite dimensional vectors that is provable, which means that the approximation is provably close to the real vector with a given precision with a given number of features and a number of dimensions dependent on the precision we want. And so what we will do with this RFTs is that we will use them for planning, use the approximations for planning in polynomial time.
Just a quick question about the last slide. So can you just remind me, are linear MDPs also captured in this model?
No, it's if you want
actually, like, if you just choose H to be the, oh, I see. So here H must be the radial basis. So yeah. I was going to say if H is the linear kernel, then this is literally linear MDP, right?
Yes, but actually when you want to go for distributions that model some real MDPs with continuous state actions, I think you need to go for infinite dimensional features, like for RKHS. So,
but actually, I have a different answer, and probably like in our audience, there's someone who knows this better. But so there are many works that extend linear MDPs by considering kernelized version of linear MDPs, and I believe when you write their transition structure down, I may be wrong, but this is somewhere like maybe the audience can help me. As far as I remember, it looks basically the same as what you write on here, where the choice of the RKHS is just up to you, which could be infinite dimensional, could be radial basis as well. Can you are you aware of that line of work, or can you comment on what's different, or why what you're doing here is not subsumed by that line of work?
Yes. So I'm aware of extensions of linear MDPs that go into the RKHS setting. The key difference is that in those papers, I think the focus is less on having tractable algorithms. So if you look at the planning section of those algorithms, it's basically optimism, which means that you won't. It's not really. I mean, it's not discussed whether it is possible to implement it in polynomial time. Whereas here, what I'm doing with this is, since I have specifically the RBF kernel, I can use this random Fourier features. But this is not this property is not only it does not only hold for the RBF kernel. It actually holds for any. There is a class of kernels that it holds for, but basically the largest one is shift invariant kernels. So if you have a kernel that's invariant by translation, then this holds for it. So I guess if you want to subsume this or maybe extend this work, you need to consider this the more general than this work, but more specific than the other works you were mentioning, which is kernels that are shift invariant or something. And then in that specific case, you could use this technique to have tractable planning.
Can I ask a quick question?
Sure.
Are you going to clarify what shift invariance and so on and so forth means, radial basis functions? Like, are there going to be slides about this?
Sorry?
Are you going to define rigorously what do you mean by shift invariance, radial basis functions, and so on and so forth? Are there going to be slides about this?
So the shifting, I'm not going to talk about it because it's not part of this work.
Okay.
It's just a reference to other, but it can be found in this paper by Rahimi and Brecht and some.
Okay.
But the RBF kernel is basically the squared exponential kernel. But I will have more slides. Yeah.
Okay.
I also have a related question. If you go to the previous slide, when you talk about this subsumes some of the standard linear systems, so can you be a little bit more specific about what kind of linear dynamical systems you can capture? Assume you're talking about something like LQR, LQG type things. But if we're talking about LQGs, it's like next state, the mean of next state is linear, but with like added Gaussian noise, right? So like precisely, it can handle Gaussian noise or it can handle other noise distributions.
So the noise you can handle. So the Gaussian noise, yes, you can handle it, and I think this was shown in a paper by Chaba. It's I think the no free lunch or free lunch from the noise paper. In that case, it is exactly similar to this setting, but for the exact setting of LQR with Gaussian noise. But I think that actually this would work for any noise that is part of the exponential family, which has both. So when we see the analysis later, it will be clear that the noise needs to have some concentration properties as well as anti-concentration properties. So the Gaussian noise satisfies this, but I think also Bernoulli noise or similar exponential family distributions, as I said, that have concentration properties and also anti-concentration properties. Is that clear?
Yep. Please keep going.
Okay, thanks. Okay.
Can I ask a question before we move?
Yes.
So maybe I missed it. I wonder whether this, like, if you take this linear transition with RKHS spaces, are you saying that this is more general than what you have, or less general, or they're the same? Like on the previous slide, you have a class of systems, and here you have, okay, let's forget about the word. Here you also have another class of systems. What is exactly the relationship between the two classes? Okay, on this slide, first
between this one and this linear one.
Yeah. Yep.
These are both of them are exactly the same. This is just an equivalent formulation of them.
Okay. So no matter how I choose things in the first one, I can choose here the arc edges, and no matter how I choose the arc edges here, it goes back to an exponential family.
Yes, exactly.
That's
Yeah. Yeah. So this is this is actually a special case of the RKHS version of linear MDPs.
special case or not?
It is a
General.
case.
Why is it a special case? What's special?
Because if you go to the infinite dimension, so the RKHS case, I think that this is similar to what you would expect. Basically here, I think
The radial basis function kernel restriction. Yeah, that's what you're talking about. That's a restriction. So it's like the Gaussian kernel. But on the previous slide, where is that coming from? That's coming from the form of the what?
Yeah, it basically just comes from the fact that we have this bilinear product here in the exponent.
Okay.
What can be done? Basically, the way this relates to the exponential to the Gaussian kernel is that you could easily write this bilinear product as the squared difference between psi of s tilde minus this m theta of phi plus some additional terms that do not couple s tilde with SNA. So the additional terms are basically either they depend on s tilde or they depend on SNA only, which means that the basic term is just the Gaussian kernel plus some additional terms.
The interaction between s tilde and SA is through this. Yeah.
Yes. Yeah. So this is why it relates to that.
Okay.
Yeah. So in this sense, this is a special case of the.
I see.
Yes. Okay. So next, I will talk about the algorithm and why it offers tractable exploration and planning, and how we improve the analysis over the existing work. Okay. So as inputs, we have the probability, the failure rate delta. We have constants that I will detail later. But basically, the constants here, alpha p, is some measure about the anti-concentration of the distribution, or maybe like the level of noise. If we had an LQR system, it is the level of noise that the minimum level of noise that is added. Eta is the regularization that we need for the maximum likelihood estimation, and xk are coefficients that we will need to choose to have a proper regret bound. So the algorithm proceeds in the following manner. For every episode, the agent starts by sampling a noise, which is a Gaussian noise, centered Gaussian noise with variance that is proportional to this constant times this matrix, which is basically a design matrix in this case. So in linear regression, this would be just the sum of x transpose. And in this case, it is merely with up to some constants, it's the design matrix for this specific family. And given this specific noise, we can perturb the reward parameter that we have for this family in the following manner. So basically, this theta hat is the maximum likelihood estimate, and this is a perturbed version of this maximum likelihood estimate. So the algorithm is based on randomized least square value iteration. So if you are familiar with the algorithm, you know that in that algorithm as well, they have this this perturbation of the reward. Okay, so then since we said that RFGs allow us to have the finite dimensional approximation, then we can compute the Bellman recursion step using the finite dimensional approximation. So this is doable. And then we interact with the greedy policy that we obtain. And finally, we update the penalized maximum likelihood estimators. Theta hat P, which is the estimate for the transition, and theta hat R, which is this estimate for the reward. Okay, so this is the algorithm, the formal statement of the algorithm.
Can you say it again? What are the capital A's in that noise equation? You have two A's, like there's AI AJ later, and there's a A in another font in the front.
Yes. So A is basically the matrix where you have it's this middle matrix. It's the matrix where you have in entry IJ, it is AI transpose AJ. Is that so?
I guess the question is, what are these matrices? Who sets them and how?
Yeah, I can go back to the model, but the matrices AI were assumed to be known. So basically, this M theta, which is the middle matrix, was assumed to be sum of theta I AI. So this is a d-dimensional mixture of matrices AI. But if we want to consider the full range of matrices, then we can assume that the AI, like the sum of theta I, is just like the entire square matrix is a parameter. And so we would have like a d squared.
I guess we just all missed it.
Yeah,
Right.
we can replace it by a parameter if you want. But
It's
yes.
But there's still that the first A in a different font. What is that? In the algorithm. Yeah, eta over alpha p times A. What is that A?
Yes, it's just just 1 second so I can be sure that I'm not saying anything wrong. But A is just I need to verify, but I think it is the matrix where we have entries. The IJ entry is AI transpose transpose AJ, but yeah, I think it is. It's basically just these are the features. These are the features that we get at time h, and usually we add the same thing times the identity matrix for regularization, and this is the regularization part times the same thing, AI transpose AJ. So it's just what happens if you replace this by the identity matrix. But it's just the AI transpose AJ in entry IJ.
Okay.
Yeah, so this is just the regularization that is usually there when we use the penalization in the maximum likelihood estimation. And in this case, the penalization we use is the trace norm penalty, which is just the trace of AI transpose AJ. I don't know if I can share the paper, but in the paper it's given in more detail. This is basically just the matrix that comes from the trace norm penalty.
Okay.
Yeah. Okay. Yes, so this is the algorithm. Okay, so some insights on why we say this algorithm is tractable. For the estimation of parameters, we use penalized maximum likelihood. So this penalized maximum likelihood is explicit for some simple distributions. So you can see this reference for more information. And there are also many techniques to approximate the maximum likelihood estimation in case it is not explicit. So there are some works, some even very recent ones that use the same representation by using score matching on top. There are also some MCMC techniques and even some simulation annealing techniques that can be used. So we consider more or less that this part can be approximated. Actually, some of these papers even have not only, actually many of them have theoretical results for a provable approximation of the maximum likelihood estimate in finite time. For the exploration, as we saw, we use this random perturbation of the reward. So there is no optimism, which means that it is tractable. It's a simple noise addition. For planning, as we said, we use random Fourier transforms. So these provide a finite dimensional approximation of our transition function and the reward function, which allows for a finite dimensional approximation of the Bellman backtracking procedure. And if we actually want to choose the precision for this approximation by optimizing the regret terms, the subsequent regret terms, we find that planning can be done in this polynomial time. So this is explained in more detail in the paper, but basically by just by calibrating the precision we want, we end up with this planning complexity.
Any reason why your planning time doesn't depend on the dimensionality?
Well, actually, there are the dimensionalities in here. They are hidden in the big O, but I don't know for what reason I only chose the H and K. But yeah, it is in the hidden in the big O. But it depends on it polynomially as well. The full expression is in the paper, but it depends on it polynomially. But basically, to provide an intuition, to use RFTs, if you want an error of epsilon, you need, I believe, 1 over epsilon squared dimensions to have an error of epsilon. So still with the dimensionality and everything, it's still just a polynomial time in all problem parameters. Okay. So now we move to the analysis part. And of course, if we want to obtain some regret bound, we need some smoothness assumptions. So the one we use in this paper is a standard one. It's that the eigenvalues of the Hessian of the partition function are bounded above and below. So what this means, if we take the example of a nil QR with a Gaussian with a noise, this assumes that we have concentration and anti-concentration of the noise. This is basically this assumption, which in terms can mean that we have both some measure of smoothness, maybe slightly weaker than Lipschitzness of the transition, and also some measure of variability, some lower bound on the variance of the value function or something. So some anti-concentration measure to be exact. And then with this assumption, we are able to show the following theorem. So basically, if we define this, as I called it before, the design matrix, this like instantaneous design matrix, which is phi the features that we had before, and A the matrix that we chose in the representation. If we define this and A as the trace norm of the matrix A that we chose before, then under this assumption and some other boundedness assumptions which are standard, like the expected reward is in 0, 1, and we choose the noise that we add appropriately. So appropriately in the proof, we show that it's sufficient to have this level of noise. Then with high probability, we have that the regret is of this order, which is square root d cube h cube k. And this hides some constants and some logarithmic terms. And of course, it also depends on some parameters that come from this assumption. Okay. So next, we wanted to assess whether the optimality of this algorithm. Minor problem, there is no lower bound for, at least to my knowledge, there is no lower bound for episodic RL with continuous state action spaces. I think there have been some recently in deterministic MDPs, but none that are explicit for continuous state actions. So the one that is known is for tabular RL. So we want to compare to tabular reinforcement learning.
Yeah, like, do you have a question? Because you mentioned this kind of second time that continuous state action is somehow separate. Maybe the action is separate, but if I have a continuous state space, then maybe it is just composed of this finitely many clusters of states that are behaving completely identically. And it appears to me that it's continuous state, but it's actually a finite state MDP. That could also be a linear MDP and so on and so forth. So it's like, what do you mean by continuous state MDP? If this is not included or this is included, I'm just lost and like somehow I'm confused about these statements.
So initially, I just meant the general version of continuous state.
Right, like there is no restriction on transitions, then I can just do this, right? Like I take a finite MDP and I kind of embed it into in an overcomplete fashion in a continuous space. Why not? Can do that.
Yes. Yeah.
And it appears to be a continuous state MDP, so it satisfies that definition.
Yes.
Of course, underneath it's finite, but
yes.
So the lower bounds would apply because of this embedding.
I agree, but maybe a more appropriate definition of this continuous state space is that maybe I don't know if a minimal representation can be defined, but the minimal representation must not be discrete. I don't know how to express it, but this is just the general.
Do you want to put some restrictions on this continuous things, because otherwise I can embed any quadratic finite state MDP in a continuous space.
I think maybe what Reda means is, I mean, yeah, if you do that, I think you will obviously get a scaling with S, right? And given that the continuous state can just accommodate arbitrary large S, pretty much get a vacuous lower bound. So you want something tighter, then it will require some additional structure, right?
Yeah.
Yeah.
This is like, well, I understand.
Yeah. I mean, even if you add the smoothness, I think there's still a way, like essentially you can just do packing and you can still embed a finite state MDP and you get a cursive dimensionality, right? So,
so maybe these bounds are not written down, but it's like pretty obvious here how to do it.
It might be somewhere, but
I might also guess that it's somewhere, because I do remember a bunch of papers that do this. So
yes. Yeah. So what I meant is just for the general case, I'm not aware of any lower bound. But for tabular RL, there is a lower bound. So to compare to this tabular RL literature, the first thing to do is to obtain an upper bound for this specific case with our algorithm. So thanks to this result by Amari, we know that a tabular MDP can be represented in this way, which in terms means that this can be represented as an MDP from the bilinear exponential family with the number of dimensions that is S squared times A. So this might not be the most efficient representation, but it is a representation for tabular MDPs. So I forgot to explain before, but the alpha and beta we have that we had in the algorithm, we had an alpha at some point, is, as I said, the anti-concentration. So if we go back to this assumption, the eigenvalues of the Hessian of the partition function are bounded above and below. So below they are bounded by alpha, and above they are bounded by beta. And this is exactly proportional. So if we had a Gaussian, then both of them are proportional to the variance of that Gaussian. And if we had some noise that has some concentration parameter and some anti-concentration parameter, then the below bound is proportional to the anti-concentration, and the above bound is proportional to the variance or the concentration parameter. So this is why I'm mentioning this alpha and beta, because they appear in the bounds, and we need to know some bound on alpha for the algorithm. So alpha and beta from our assumptions in this specific tabular case are the minimum and maximum of these quantities, which are just come from this representation of the tabular MDP. So if we assume that this has a minimum value that is strictly positive and a maximum value, actually this has a maximum value, I think, which is 1/4. We just need in this case to assume that it has a minimum value. Then our algorithm satisfies this bound, which is proportional to this quantity times h³ k. And
so this minimum eigenvalue assumption is saying essentially that you have to go everywhere in the state space with some positive probability or something like that.
This definitely reminds of the reachability type assumptions, right? So I was wondering how you can translate that to that, because in MDP, there's a pretty common assumption that says for every state, if you, actually I think, yeah, it's a little different. So the usual notion of reachability is that for every state, if you choose the policy that maximizes the probability of reaching that state, how much you get, right? So that's already a pretty strong assumption, but I think you're talking about something even stronger because you don't have a max over pi here. So I was trying to break it down. It seems to be related to this reachability kind of, or minimum visitation probability kind of parameter, but it's not maximize the overall policies. It's for all state action pair, you start from like every state action pair needs to reach every other state.
It's not completely that. It's about the variability of the transition, actually, because basically the way alpha and beta appear is that we will use this p theta to define the value function, and then we will want to have a first order approximation of p theta. So in order to have some precision over that approximation, we need to assume that basically the variability of p theta, or this second order derivative, which is what makes appear the Hessian of the log partition function, we need to make sure that that is a smooth function. So the Hessian has an upper and lower bound on the eigenvalues. So it's not it's weaker than assuming that you visit all state actions. It just says that if you change this parameter theta slightly, then
wait, I think it's not weaker. It's almost that, right? Because if you look at this expression, the exp theta ijk can be basically interpreted as an unnormalized version of probability of state I starting from jk state action pair, right? So if you just but this term directly appears on the numerator of the alpha and beta definition. So upshot is that if there is a state action pair,
yes,
and a next state S prime such that S prime given SA is equal to 0, then beta becomes 0.
I would think so too.
Yes, in this specific case, it is true. In this specific tabular case, but as I said, this is not necessarily the best representation you could have for a tabular MDP. But in the general case, if you look at the expressions of alpha and beta, which are just the Hessian, the minimum and maximum eigenvalues of the Hessian, then it's not directly related to the value of p theta. I mean, the Hessian could be 0 at some point without the probability.
If we want to interpret these results, then maybe we should try to get the best interpretation, or like the best representation for the tabular case. And so I'm not sure whether you're saying that you know of a better representation which doesn't suffer from this problem, or this is what we know, and at a problem we do have this problem that with this representation, if an X state is not accessible, then your beta is going to be 0. Which limits the applicability with this representation. We don't rule out that there is something else, but like, do we know of anything else that would allow 0 transition properties? I think I know. Like, if it's more like assuming that you know the support. So if you knew the support, then with the AI matrices you could make it happen. But if the support is allowed to change, then I don't know how to make it work.
Actually, it's not even the support in this case. So if we take another example, which is LQR, you can assume that your linear function is whatever you want, and then add a Gaussian noise with some variance sigma squared. Then alpha and beta are beta is sigma, and alpha I think is sigma over square root d or something like this. So it's really completely independent from. I mean, it's not. In this case, still, since you have the Gaussian distribution, you have
like homoscedastic versus heteroscedastic noise kind of thing. It's like if you have a very heteroscedastic noise, that depending on where you are, what action you take, maybe your noise completely goes away. So you don't have any noise. Like you know exactly you're not going to reach this state under the parameter. Then that's ruled out. As a function of the parameter, the noise variance changes like drastically from 0 to something positive, then that's a bad thing. So something like that. Is that what you're saying? If you have roughly homoscedastic noise, then we should be okay. So the assumption is essentially saying something like this. It allows some heteroscedasticity, but like not extreme. And in tabular MDPs, we see extreme heteroscedasticity.
Also, I just want to jump in. Maybe for the sake of time, we can let Reda finish the presentation, and then we can ask more questions near the end. Again, yeah, sure. Maybe if you can try to finish in like 10 or so minutes, that'll be good.
Yes, okay. We can discuss at the end then. Sorry.
Yeah.
Okay, so the purpose of this example was not to show that this BEF is the perfect representation for the tabular MDPs. It's just to show that if we use it, then we would have this type of bound. And comparing with the lower bound of Dominguez et al. 2021, so this is the lower bound they have. So we can conclude that the bound, at least in this case, is tight in its dependence on H and K. We can talk about the dependence on the dimensionality at the end if you want, but we have some. We still have some doubts in the general case for the BF, whether this is the optimal bound or not. Okay, so I'll briefly talk about some interesting components of the proof. Namely, there are 3 parts: a non-concentration, a transportation inequality, and a linear regression trick. So the first part is just to give some credit to the RLSVI style of algorithms. So basically, just traditionally, we have when we have the regret decomposition, then we have this approximation error as part of the decomposition, and we usually decompose it further as this learner error plus this difference between the optimism and the estimation. And we get rid of this first term by assuming optimism. So if we have with high probability, this is a negative term, then we just assume that this goes away with optimism. In the RLSVI style of algorithms, since we only have a perturbation of the rewards, then we can only obtain that we have this optimism with some constant probability in U. So this is only a constant probability and not necessarily a high probability. Now, if we were in the discrete state action spaces, there are actually ways to go from this. If we can ensure this thing, then there are ways to go to this high probability. But in the continuous space, I'm not aware of any technique that allows algorithmic techniques that allows us to go from this fixed constant probability of optimism to a high probability. And basically, in this style of algorithms, we can show that it is enough to this constant probability is enough to bound the learning error. And this was first done by Zanet et al. In 2020, who obtained a frequentist regret bound for this RLSVI. Okay, so just the takeaway: full optimism sometimes is intractable. RLSVI can be more realistic under the proper assumptions. The second part is this transportation lemma. So usually in the proof, in RL theory, at some point we need to relate the value function error to the model error, if we have a model-based approach, of course. So traditionally, what is done is this simulation lemma. I cited one paper, but it is done in a lot of different papers. And so basically, it takes this form. we want to go to bound this this difference, and we want to bound it as a function of this difference that depends on the transitions, and we obtain this type of inequality. Now, a nicer inequality is this transportation inequality, again from Amari et al., from the concentration inequalities book. And basically it says that if you have a function such that its span and its variance under this transition P are finite, then for every Q that is absolutely continuous with respect to P, then we can have this type of inequalities. And basically we have this, this is the leading term, which is H square root of KL. And this KL can be directly compared to what we have in the inside, and H is smaller than H to 3 over 2. So this is a nicer way of having of relating the value error to the model error. Also, as a bonus point, the KL divergence actually pairs very good with the exponential family, since the KL of an exponential family is just the linear, it linearizes the exponential family. So the takeaway is that this is a nicer way of handling this transition, and it reduces the square root of H compared to using the simulation lemma. Okay, and the last part of the proof that I think is interesting is how to remove clipping from the algorithm. So I think this is also a nice contribution in the paper. So usually, basically, we need to have some clipping of the value function in this interval 0h. This is crucial for the simulation lemma and also for some other parts of the proof. But the problem is that this adds this extra nonlinearity. So if we had this clipping in our algorithm, still the planning part would not be tractable, because we would have that minimum and then the integral. And so yes, this is still something that should be avoided. Now, how do we do it? This is thanks to a result that exists in the bandit algorithms book by Latimore and Sepavari in 2020. Basically, in this book, this is a linear regression. It can be thought of as a linear regression result. And what it says is that, so basically, if you have n vectors and you want to do linear regression, and you have this design matrix VT, which is just some regularization plus the sum of vector transpose, then the number of times that the norm of your vector in the design matrix at that time will be larger than 1. This number of time is bounded by something that only depends on D and the bounds that you have on your AT and the regularization. So it's independent of time, which means that this is a finite amount of times. Why this is interesting in our case? It's because we have this estimation of the value function in the same case as a linear regression problem. And this result would entail that the norm of features can only be large a finite amount of times that only depends on D. And this is interesting because it means that essentially we don't need clipping, because the number of times that the value function will be outside of this range is finite. So we can omit clipping without adding anything in the algorithm by just adding this part in the proof. Okay, so to conclude, for episodic RL with the BEF, we propose this algorithm that has this Frequentist graph bound. We show that tractable planning and exploration are possible in this specific case of continuous state action spaces, MDPs. And for linear RL analysis, we think that this can be of broader interest, this no clipping technique of just adding this part to the proof of existing papers. And some possible extensions that I think could be nice are to investigate the increased dependence on dimensionality. So some recent papers that I saw that are still preprints or under review, they try to analyze this to see if it is the price of tractability. this increased dependence, which is d to the power 3/2, instead of having a linear dependence on dimensionality. Also, we would like to have some experimental evaluations in the future, and another possible extension is to have other models than this RBF kernel, which is to just move to any, as I said before, shift invariant kernel or other types of kernel for which the RFT approximation holds. Okay, that is all. Thank you for your time, and here if you have any questions.
Okay, let's thank our speakers. Okay, now we can ask questions. I guess I'll start with one that I wanted to ask when we talk about the alpha beta stuff. So given that you need to assume that there, the small one, the beta need to be bounded away from 0, I assume that actually your bound the alpha and beta will actually enter your bound. Can you briefly comment on how your bound depends on these two parameters?
So in the final bound, we have some polynomial dependence on beta over alpha.
Okay, got it. Okay.
Yeah, which is I think which is usually what we have in many other papers. Usually you have the 1/sigma dependence, I guess, or h/sigma dependence. If you
right, my understanding of the reason you need that is that because you're doing only perturbation, you sort of need the system dynamics to be noisy enough that you actually rely on that to do exploration for you instead of your algorithm doing exploration on its own. Is that a fair interpretation?
So basically, the idea is that you need it to yes, you need it to ensure that when you add this noise, then it is enough for exploration. You still need to add the noise. It does not do exploration for you, but it means that if you have this added noise, then it is enough to explore with constant probability.
Okay. I have one more question, but if there's anyone from the audience who would like to ask, please go ahead. Because I feel I've asked too many.
No, you haven't.
Okay. Yeah, just one more. So I'm curious because I just reminded myself of the Andrea Zanet and L's RL SVI analysis paper. So their paper is a purely frequentist bound without any reachability type assumptions, right? And the key argument, as you mentioned, is that if perturbation allows you to have constant optimism probability, it translates to a high probability bound. So you also mentioned that in your analysis, but I'm wondering, like, because as you mentioned, like as we discussed, when we translate the assumptions in the tabular case, you would require some kind of, you can go from any state action pair to any other state kind of assumptions, but that paper wouldn't need these kind of assumptions. So I was wondering, like, you mentioned this constant optimism probability. So which part will break down if you try to follow that argument? If you don't have the assumption on alpha and beta, is it that you cannot establish that your estimate would be optimistic with constant probability, or you can establish that, but even with that, you cannot bound the learning error?
You cannot have that constant probability because so basically when you want to express the key idea in the proof is that you so when you have this learning error to analyze, what you do, since you have this parameterization, then you do I don't remember exactly if it's a first order or second order approximation, just Taylor approximation, and then using the fact that you have this minimum level of variability of the value function that comes from alpha, then that's what gives you what gives you the NCHI concentration or the probability, this result basically.
New parameter, yeah. Okay.
Yes, so you do need it, and I think it's still similar to the assumptions that are made in Zanet's paper, because so maybe if I can share a different.
I don't see any significant assumption in that paper, especially if you applied it in the paper.
It is due to the nature, to the linear model that they assume. Okay. So to talk explicitly about alpha and beta, where is the proof? Yes. So we also have this C. So if you remember, we have the psi and phi that are the features. We define this matrix, which is like the variance of psi, the variability of psi under this p theta transition mapping. So we define this matrix, and basically the alpha and beta are defined in this way. So the eigenvalues of this matrix C are lower bounded and upper bounded by alpha p and beta p. So, and for the reward as well, there is a similar condition. And basically what this means is that if you I mean, the only reason we need this is that when we move from when we change theta slightly, then we also guarantee a slight change of the value function. So initially, it is a slight change of the transition and of the reward. But then why we need it is that we need to guarantee that if you perturb the theta parameter, then you also have a minimum variability of the value function, because otherwise you wouldn't be able to distinguish two parameters.
Oh, but if two parameters differ in such an insignificant way, do you really want to distinguish between them? So wouldn't the analysis be like, wouldn't it be possible to rewrite the analysis to kind of account for this and like just try to distinguish what you need to distinguish? Maybe let's do the analysis in, I don't know, value function space instead of parameter space or something like that.
Yes, I think if we wanted to do it in the value function space, this would be something like a Fisher information condition type of a. Yeah, I'm not sure if it's more general or more specific, but I think it should lead to something similar to having like a condition on the Fisher information matrix directly.
Yeah, got it. So what you currently have is similar to the Fisher information, which like you want to have a regular model, but identifiability of the parameter is not a problem. And you are basically recovering conditions for that. Whereas, yeah, maybe the analysis can be changed so that this is not actually required, because intuitively it shouldn't be required.
Yeah, probably if you wanted to have like some minimal precision that is not important, which depends on the regress bound at the end or on the horizon, then yes, the analysis definitely could be adapted. Because then if you don't detect that small variability, then it's not a big problem at the end. But
I mean, the metric of variability should be like how much the value functions are impacted by that variability. If they don't have any impact, then who cares?
Well, on principle, I do agree, but then you would need some structure to be able to know that it's not the value function that didn't change. It's just that the change is so small that you don't see it or something. I mean, you need some measure. You need to either say that you know beforehand that you don't care about some level of change, or you know that starting from some level of change, from some sensitivity, yeah, basically you need to define your sensitivity at the beginning.
Why? I don't care about identifying theta at all.
Yes, but this is, I mean, in this case, it is a parametric model. So theta is what allows you to determine V. But if you wanted to have like a model-free approach or something, then yes, you only need to determine V at some point, yes.
I'm not sure we agree on this. Maybe it's future work. It's not unclear whether, like, I suspect that the algorithm might actually work for these unidentifiable cases as well. It is just that the proof is not supporting it now. And maybe there is another proof that will just be applicable to this algorithm that avoids this condition, because it seems to me that, like, it's an artificial condition. It's like, one evidence of this is that in the tabular setting, we don't see anything similar. And we have a proof that the algorithm works. Basically, the same algorithm. I would say the same algorithm. Isn't it the same? It's the same algorithm, right? Same setting. So that kind of clearly shows that this is an artifact of the proof. This is not a criticism. Like, I wouldn't be able to do even this proof, but but there is some work to be done. Perhaps.
Yeah, unless you have a right. I think like another way to close this question is like if you can come up with an algorithm-specific counterexample to show that this algorithm literally breaks down in an instance under beta equals 0 or something, right? So that'll also close this question. But without that, I think it's reasonable. I agree with Trevor. It's reasonable to suspect that maybe just a better analysis could avoid dependence on these assumptions.
I'm not sure about the alpha dependence, because if you don't have optimism, you still need to find some. I mean, it depends on your structure again, but you need to have some assumption, some structural assumption that tells you how to explore the space. So if you don't have this alpha, you don't know if adding a noise would be enough. You would need to. I mean, in the general case, I would assume that you would have some more involved way of doing the analysis of exploring the space, like.
Let's see. I hear you.
In some not simpler but some more understood cases like deterministic MDPs, what is done to explore smartly than the optimism is to have this information directed sampling kind of things. But if you cannot do this thing because you don't have a lower bound, then I'm not sure if it's straightforward to explore in your
Oh, I mean, I don't think any of us is saying that it's straightforward, but it's that it's left as a possibility.
Yes.
Actually, there is a question in the chat. Just noticed.
Yeah, there's a question on the chat. Paul, do you want to say it for yourself, or I can read it out if it's. So the question. Oh, okay. Bo, okay. Yeah. Okay, so Bo has a question. So it's saying the random feature approximation error in Rahimi and Rect is not for infinite norm. So in some sense, he guesses that there will be some volume or ratio dependency in the error due to the random feature approximation.
Yes, but that's why we have the bounds on the features. So the features are bounded in this case, which means that even though the state action space might be infinite, the features are bounded.
Okay. Are we supposed to go off recording at this time?
Yeah.
We can stop recording.
Okay.